Okay, so last presentation of today and last presentation of Kaggle Days Paris 2022. Very exciting topic, item matching by Theo Wiel. Let me tell you a bit more about Theo. Actually, Theo came here as a champion. Like 2 weeks ago, he won the Kaggle Days Championships. We met in Barcelona, so congratulations. And I was very glad because I thought that maybe he will use a couple of minutes to tell you how he won. But it wasn't on item matching, but he won 2 competitions at the same time. But coming back to Theo, he asked me not to be very long. He asked me to tell the best bits. So. He's a triple Kaggle Grandmaster in competitions, of course, notebooks and discussions. And actually, he was the 3rd triple Grandmaster in France. Is it true? Yeah, amazing. Lately, he joined NVIDIA, like lately, a month ago, right? And now he's working with Jean-Francois. So very strong team over there, 28 medals, impressive. And as I said today, item matching. Was I short? Okay. Oh. And I was supposed to say that his image on Kaggle is smiling cat. Okay, that's all. Thank you.
Thanks, Maria. Hi, everyone. Glad to be presenting here. I see that I'm the last one, so I won't be holding you for too long. So the topic is item matching. I will just provide. Okay. It has a bit of delay, so whatever. I will provide quickly the overview. We'll be discussing basically what is item matching. And then I will present 2 approaches. I mean, there are a lot of ways to approach the problem, but these are the 2 ways we've seen recently on Kaggle Competitions. And as Kaggle is a great place to steal ideas and adapt them to your problems, I will be reusing those pipelines. So about the introduction, we will cover basically what is item matching. I'm sure some of you are very familiar with what it is. So I will be quickly covering that. Then some use case, how to validate problems, how to validate with such problems, because it's important. If you don't do proper validation, you can't build proper models. So you need to ask yourself the good questions. And as I said, there are a few approaches, but I will also cover complexity because, well, we'll discuss that, but it's a tricky problem. So what's item matching? Item matching is kind of like classification, but not really, because it's classification with many, many classes, and sometimes only 1 instance per class, and even sometimes classes that you've never seen before in the test data. And your goal is from raw data to find the matches. What are matches? Matches are items that refer to the same class or to the same object or whatever you want to call it. And basically, you want to build a graph which vertices indicate that 2 items are the same. Quite simple, right? Some use case example. So no bubble on the faces, sorry about that. But the image is from Vuitton, so I think we'll be fine. Let's say I have this picture of an Instagram model, and I know that she is wearing a bag. And what I want to do is, given a database of Louis Vuitton bags, I want to know which one she is wearing. So what I will do is check the bag and basically score it against a database of possible candidates. And when I retrieve the best candidates, I can, for instance, put it in an ad or put a link for the viewer to purchase the bag. Next use case, once again, this is completely random. I don't know if they actually do that. I don't work for Louis Vuitton. Is if you have a database, for instance, for Sephora, and you have listing of prices. And sometimes, you know, database, especially in big companies, they get inconsistent. And you want to find those inconsistencies because it can be an issue. If you sell the same perfume twice for different prices, well, that's not good because you're basically losing money or either losing customers. And here on these 4 examples, we can already see that it's a complicated topic because items are similar, it's tricky, and you need a lot of domain knowledge. And as I said, I come from Kaggle, basically. So I know Kaggle Competitions, and there were a lot of interesting Kaggle Competitions. First one, you have images of whale or dolphin fins, and you need to find to whom it belongs, to which dolphin it belongs, or whale. Second one is a Shopee price match guarantee, which is quite similar to the previous topic with Sephora. We want to find listings of items that refer to the same object. The Google landmark retrieval one, we need to find which landmark is on the picture, and the Foursquare location matching, which I will be covering later because I did this one, so I know it a bit. About validation, there are two ways to validate your model, and as I said, they are problem dependent. Basically, either you want to evaluate, again, unseen items, because you're assuming that during inference or during prediction, you will see new items that you've never seen before. Or either you don't want that. Classical application is set on the case where you have no new items, you want to match the item in an existing database and find in a given database which item is the most similar. And on the other one, you want to find duplicates, basically. Yeah, I will talk quickly about the greedy approach, but because sometimes it just works. So you have a bunch of items, remember the graph, and you want to basically build vertices between nodes, remember? So to build vertices, you take all the nodes and you loop over all the possible pairs. And once you get a score for each pair, you can basically select the ones that are above a given threshold and infer matches. It seems quite simple, and sometimes it works. But the issue with the greedy approach is that when you score all possible pairs, you have n-square pairs. So what we are going to want to do is to find a set of candidates that are good enough to guarantee that we can save some computational time without losing in performances. And another way to consider the topic is just to take all your data. You want to find a space in which your data is meaningfully represented, and then retrieve all matches using nearest neighbors techniques. About complexity, as I just said, the greedy approach is in order n square, O of n square, where n is the number of items. And if you actually perform retrieval scoring, you do retrieval in O of n square as well, and scoring in O of n times k, where k is the number of candidates. And with matching, matching is order n times n square as well. But is it really actually? Of course not, because otherwise we won't be doing item matching. The greedy approach, I can already discard it, because if you have a true database with, say, 10,000 items, it's already in the order of millions, so it's not tractable. And actually, the trick is that if you retrieve items with k and n, for instance, or if you have an embedding, the retrieval is not of square complexity. If you use a correct algorithm, which are easily available anywhere, like on scikit-learn or on your favorite library, you can do it in a linear time. And then, with the retrieve and score approach, the complexity comes from the scoring model, which once again is order O of n times k. And the embedding and matching problem, this complexity only comes from the embedding you are computing. And actually, if you have a GPU, which I'm sure most of you do, using KNN is super fast because you have interesting libraries which perform accelerations. To name a few, you have FACE and CUML. So I recommend you forget about scikit-learn and use it instead. So you will be able to tackle much more complicated problems. Okay, moving on to the first approach. So you will see a lot of names in the literature. The first step, once again, is retrieval, is the selection of good candidates. You can call it blocking or matching. And the second step is classification or scoring of those candidates, which we can also call deduplication. And I will provide some example. So retrieval, the idea is that you want to build a set of good candidates, but you don't want to miss any positive matches. And the fewer false positive you have, the better your retrieval model is. Because if you retrieve, say, 200 items, and among them only one is a positive, you are building a way too hard problem, which is unbalanced, and you will struggle later on. And the fewer candidates, the lowest the compute cost of the next step. It's really problem dependent, and with enough background knowledge, you can easily find clear rules to build a good set of candidates. In that case, I use a color proximity rule, but we will see that it can easily be adapted to anything. And then scoring, I mean, it's quite easy once you have your pairs, because if it's a true match, then the label is 1, and if it's not, the label is 0, and you feed it to your favorite model. It can be XGBoost, CNNs, transformers, depending on the data, and you predict the probabilities. And therefore, once again, you can retrieve matches. And with some graph processing techniques, you build back the graph, and it's done. You've solved your problem. I mean, almost. So this might sound a bit complicated, so I'll be going through the Foursquare location matching example. So this was a competition in which we had a POI IDs provided like from some Google Maps API or similar, and we needed to find which IDs refer to the same place. And obviously, there is those in the data, because what we have access to is what the user inputs, for instance, on Google Maps. They basically name the address, the city, and everything about the let's say, restaurant. They give the URL of the website, the phone number, and a provided category. But we also know where the user is locating the thingy, so we have the latitude and longitude. And already when you have position data, it's fairly easy to retrieve nearest neighbors, because using latitude and longitude, basically you can know which points are nearby, and this builds a good set of candidates. But as I said, there is noise. So if the latitude is wrong, you will miss the candidate. So you can also consider the other columns. And that's where it becomes a bit tricky, because other columns are text data. So you need to embed them in the good space, or either consider string distances to build the candidates. But remember, the key is to keep the approach not too computationally heavy. You want to avoid like big computation in n-square complexity. And then once you have pairs, let's say we have 2 rows we selected as a good candidate, you either build features on all the columns to feed to a tabular data model like XGBoost, or you can also feed all the strings to a transformer, and you retrieve the score, and you have your first pipeline for item matching. I will then go through the solutions of the competition to show you that even though it seems simple, you may want to complicate things a bit. This is a bit specific to Kaggle, but this applies also in production, because in this context, we had limited inference time. And so what the first place did is first retrieve features using the position on the one end, and on the other end, they retrieve neighbors using better biddings. They use a lot of candidates actually, like 100 per models, but they use the first model to filter those candidates and reduce the number of items to 20. And this is actually key, because with fewer candidates for the next model, you can fit a lot more stuff in the model, like build bigger models, and still respect the 9-hour delay. And then they built a third model, with, which is a more complicated like GBM. And then they build a fourth model, actually three fourth model, which are transformers, but also a cat boost. And these models are even slower to run, but as the other two models it's featuring, they can run on the pipeline. And then I don't know why, but they decided to put another model which does post-processing and finally merge prediction. So this pipeline is quite complicated, and it's something that you will see on Kaggle. But the idea you need to keep in mind is that if you have a simple model to reduce complexity, then you can use huge transformers and still have an efficient pipeline. For reference, this is a pipeline used by a second-page solution. So it's quite hard to understand, but the idea is the same. It's every step, you add another model, you filter down the number of candidates, and since you have fewer candidates, you can add another complicated model on top. And in the end, just blend everything and you've got your solution. I will be then discussing the second approach, which is the embed and match one. I think I'm a bit too quick, so I will slow down a bit. The embed and match idea, as I said, is that you want to find a space which is a good representation of your data, in which you can easily retrieve neighbors using a simple algorithm like KNN. The goal of the representation is obviously to have similar items have close vectors and different one be further away. This way KNN will work well. And actually what can work is you just use your pre-trained favorite CNN and feed the dolphin images to it, and you will find an embedding. And this embedding works for retrieving dolphins. But if you want to differentiate different kind of dolphins, you will get issues, which is why you will need to fine-tune this model. One of the ways of fine-tuning such model is to use a triplet loss. The triplet loss idea is quite simple. You will feed triplets of images to the network. One is a reference image X. The other one is a positive result X plus, which is an image of the same class. And another one is a negative example X minus, which is going to be an opposite, a negative image, which you don't want to mask. You don't want to match to the X query. And to do so, it's fairly easy. I mean, intuitively, you use a loss function that maximizes the distance between X and X minus while minimizing the distance between X and X plus. And that's the idea behind the triplet loss. Of course, to avoid like having exploding representations, you need to normalize everything, and which is why the representation of your loss function is not really a mean square error, but rather a cosine similarity adapted one. So triplet loss works, but in order to have it work quite well, you need to feed it meaningful examples. Let's say I want to distinguish dolphins. If I use a car as a negative example, I will never be able to distinguish between different dolphins. So that makes no sense. So you need to cleverly choose your X minus, and that's perhaps one of the hardest things to do with the triplet loss. So if you want to read the paper, it's good, recommend it. But I will move on to the next idea, which is ArcFace. Once again, a very interesting paper, quite easy to read. And the idea is fairly easy. They consider the problem as a classification one because, as I say, it's classification just with a lot of classes. And they want to focus on the last embedding learned by the problem, by the model, and make sure it obtains meaningful representation of classes. And to do so, they aim to disentangle the predictions of each classes by using, instead of a softmax with a margin between classes. So this is what they represent in 2D on the circles there. On the left is a classical softmax. You see that classes are separated, but not very distinct. The representations are too similar. And on the right hand, they use a margin M to separate the classes. And actually, the implementation is quite straightforward, with a bit of transformation on the output priorities of the model if you write them in polar coordinates and develop the softmax activation using the cross-entropy loss. You can add your margin M in the cosinus of the representation, and you've got your loss function. And the good thing is you don't even need to implement it because people did it for you already on PyTorch libraries or stuff like that. And then once you've fine-tuned your model, let's say using RFace or the triplet loss, you can plug a KNN on the output of the model and it will retrieve matches correctly. That's kind of the magic of deep learning. You don't even need to do anything, just train your model. But models are complicated to train, and especially with the arcface loss, the idea behind the overall thing is that if you start with m equals 0, you have an easy classification problem, and the higher m, the more complicated the task. And one of the tricks you see from Kaggle Competition is that they use scheduling on M. They start with a simple M to initialize the network correctly, and then they make it higher to have it being more powerful regarding the discrimination of classes. Another comment from top Kagglers is that arcface is better than triplet loss, and that's what you see on solution. Most item matching competitions are won with arcface or variants of arcface, because when a paper is good, you see a lot of researchers trying to improve it, and sometimes their approach is better, sometimes they are not, and that's your job. Your job now is to find the better approach of the arcface variation. Another important thing to do is to consider tweaking the model, the architecture, the image size, and also the head before the arcface, because it plays an important role in having a correct representation of your embeddings. You will see stuff like GEM or advanced pooling or a lot of ideas that arise from Kaggle solution. So once again, I encourage people to look at solutions of winning competitions because you'll find a lot of interesting ideas to adapt to your pipeline. And you can also do embedding stacking, which is a particularity with Kaggle. In real life, you don't want to do that because it's costly, but it works. So yeah, this is basically the pipeline that was used by most of the winning competitions of the winning solution of the Happy Whale competitions. So the Happy Whale competitions, you needed to retrieve, to identify which dolphin or which whale was on the image. And top teams use EfficientNet with arcface or something which is similar to arcface, and then nearby retrieval. Usually KNN does the job, but you may want to post-process things a bit using like graph theory or thresholding or neighbor aggregation or even more complicated stuff that I won't go into the detail on. This is a solution pipeline from the Shopping competition in which you had to find duplicated items. You were provided with text data and image data, and the top team used two models trained with the arcface loss. One is an image model, which is NFNet, and the other one is a text model, which is XLM Roberta. They concatenate the embeddings and do a bunch of post-processing to retrieve the matches. An interesting idea with their solution is that they say that it matters more to have clever post-processing on embeddings than to have a good model. So once again, go look into that. It's a bit complicated and requires a lot of tweaking, but only with the models and the KNN you have a great baseline already. This is a solution by someone who is in the room, or he left, I don't know. Oh, he's here. This is the third place solution to the Foursquare competition. So Sai used a quite clever approach regarding, I mean, what I've presented so far is that it combined the retrieval and embed technique in order to build a good set of candidates for his model. He used Roberta, which he pre-trained using ArcFace. And using this Roberta with ArcFace, you do your KNN, and you have a clever set of candidates which can be fed to a classification model like the one I described earlier. And my team, with Vincent, who is here as well, got 4th place. We use gradient boosting. So not as fancy as that, but it worked as well. So you need to try the approaches that works the best for you. Sometimes it's neural network, sometimes it's boosting. But the key with item matching is that it allows for a diversity of pipelines. And a good understanding of the problem is really what makes a difference between a good solution and an average one. Yeah, that's all. I think I talked too quick, but whatever. If you have any questions, we have a lot of time, and otherwise it's going to be upstairs and buffet.
Yeah, we have 15 minutes for questions. That's a lot.
Thank you, Theo. Just a quick question about negative sampling in triplet loss. Is it just to pick a random negative sampling from other classes, or there is other better way in order to pick the right negative sample to train the triplet loss?
That's the idea. Like in most problems, if you pick a random negative sample in a random class, it's going to be an easy sample. Let's say you want to distinguish cars and planes. If you have on one end, let's say 10 classes of cars, and on the other end, 10 classes of plane, you want to always pick a negative sample for a car in a different class of car. Otherwise, you're just going to learn about a bad embedding.
But randomly pick it from the other classes, right?
Yeah, but on a good class.
Okay.
Thank you. Thank you so much for your presentation. I actually have a question about the Wales competition, because I remember there were many images that were, like, I thought very complicated to find a match, because you can have whales in pictures where it's only ice, so very different texture, and then the same whale would be caught in, I don't know, just water, or having a mountain or greenery in the back. And I don't know, some whales were, one picture had it like very close up, some pictures were super far. So there were lots of variation, and I thought, how can I augment this data set? Did you use augmentation, or you just, I'm gonna do the best embeddings like you said, and that's it?
I did not do the competition, but I think top teams use augmentations, and augmentation actually is a good way to regularize your models. And another idea was that you could crop images on where the whale or dolphin is located. Like top teams also use bounding boxes, and a lot of ideas are possible.
Questions? Comments?
Thank you for your presentation. I used to participate in the Chopin competition, so I'm interested in how you balance the different data, for example, image and text data, how you weight the embedding from different source of data.
From what I know of the top solution, they did not weight anything. They just concatenate their embeddings, and then on top, they use neighbor retrieval. But they also do neighbor retrieval on separate type of embedding. And then it was tweaking thresholds to correctly weight everything.
So it's threshold fine tuning with.
Yeah, it's mostly fine-tuning of parameters.
Thank you.
So validate your models correctly so you can tweak thresholds.
Okay, I think that's it. Thank you so much, Theo.
Thanks,
And
Nadia.
thank you so much for your attention. This was the last presentation of today.